Let's begin with this question. So guys, I would appreciate, of course, if you participate, if you show me your faces. They're great. Rachel, good morning. Nice to see you, Christian. Anyone showing their faces so I can see your expressions of despair? This question, I mean, what's there to despair about, right? 17 minutes, my God. I mean, I could have used my head to hammer a nail into the wall at that time, right? Because that would express both my frustration and my irritation. And, you know, just when you think of something very blunt. So this, what is this thing? Tell me, please. Limit as h goes to 0 plus. This refers to measuring the yes, derivative, but derivative is a weirder word. It's a new word in your vocabulary that you might have acquired only this semester. Measuring the slope, right? Even before the tangent line, the slope of that curve locally. At what points, may I ask? So here is, if it's h plus means that I am moving slightly, a plus h plus is slightly to the right. So in the first expression, I'm measuring the slope between this and that point. So that is the line that I measure slope for. Yeah, that's the slope I measure. In particular, I just measure the slope of this line segment connecting this red dot, which is a plus, it's a plus h plus, and the second coordinate is f of a plus h, right? So it's this segment that's measured. Yes? And what is the sign of this first slope? Christian, you were almost right, you see, but what's the sign of this first slope? If h goes to 0 plus, the sign of the slope, in other words, you look at this expression and you say, it is positive, wonderful, this is a plus. Now, if I take h minus, that means that my, so I always use this black dot as one reference point. If I am using h going to 0 from the left, that means that I'm slightly below. I'm talking about this line segment, yes? And what's the slope for that line segment? It is negative. Ooh, so it's negative. So what does it say about the derivative? So this is f prime of a. What does it say about it? Does not exist. Exactly. So this derivative does not exist. Is it clear to all of you guys? It's easy. So does it take what, 20 minutes to answer this question? I hope it does not, right? I hope you were just kind of just musing about the morning and enjoying watching me eat. I'm not sure how enjoyable it is, but apparently some people don't believe I can eat food. I usually don't eat food. It's for recreational purposes. Good?
You can also just say that it's non-differentiable at
Yes.
off of it.
Yes, it's not differentiable at that point, absolutely right. Or the derivative does not exist, it's not differentiable, all absolutely correct answers, right? And take a second, because guys, do you understand what's the idea? Why the idea is so simple? Forget about complicated language. This curve is built of many tiny line segments. That's the idea. Where it's built of many tiny line segments, that's where it's differentiable. Here you can see that if I improve my partition, if I approximate by more and more line segments, it will not make this point smooth. It will not, when I zoom at this point, will not make it look like a segment of a line. You understand? So it's like what you can imagine is that you take a line and you continue breaking it, creating more and more line segments. Break it more, you create more line segments. If you can continue breaking it at this point and create more line segments, and it will look like that's at this point there is a flat line going there, then that is going to be a differentiable point. Clear? Now let's move to the next question. Here is question D2. So we have a bunch of, I have never read it actually. So f prime, g prime have the following values. Here are some values here, right? So then they ask you to find h prime of 2, where h of x is the logarithm of g of x. You understand? So you have all those sort of values. Now help me please calculate h prime of 2. It should take you, well, a minute is very generous, but you can take 2. Okay, thank you, Ping Ping. What about the rest? Okay, so 2 people say 1/5. Let's see what it is. So first of all, how do I approach it? H of x, it's a sort of implicit differentiation here. So I see that h prime of x should be the derivative of logarithm, which is 1/gx times g prime x. Do you agree? Now I need to do it in particular at the point 2. So what we have is that h prime of 2 is 1 over what g of 2? G of 2 is 5, correct? G of 2 is 5. So it's 1/5 multiplied by what's g prime of yeah, so what is g prime of 2? So g prime of 2 is minus 51. So it should be minus 51 divided by 5. Do you agree? You all said 1/5, but why? You need to take the derivative of the inner function. It's chain rule. Is it clear? So h prime of 2 is what? It's 1/g of 2. What is g of 2? I just look at here as x. X is 2. So g of 2 is 5. So 1/5 multiplied by g prime of 2. So g prime of 2 is minus 51. Agreed? Yes, don't forget, I mean, don't ignore this information. So let's now, may I erase, right? You have it. Now do the same, calculate k prime of 1. All right, guys, so we calculate k prime 1. Takes you a few moments to do it, right? Try to do it under a minute. Okay, let's see what's an answer. Okay, Rachel, let's verify what it is. So Rachel says cosine of 40 times minus 37. Let's see. So the derivative, first of all, I'll calculate k prime of x. So I have it here. So that's by chain rule cosine of 3fx plus gx multiplied by the derivative of the inner function, which is 3f prime x plus g prime x. Yeah? Good. So there is this 3 here. So what do? We simply now plug in the value. So we need it at 1. So instead of x, I plug 1. So we have k prime of 1. It's cosine of 3 times what's f of 1. I look into this column. F of 1 is minus 3. So it would be 3 multiplied by f of 1 by minus 3. Or minus 9, right? Plus g of 1. G of 1 is 49, right? So it's 49 minus 9. So that's the 40 there, right? Multiplied by 3. What's the derivative at 1? It's minus 1 plus the derivative of g at 1. It's minus 36. Good. So the answer for k prime 1, it's cosine of 40 times, what is it? It's minus 36, yeah. So so it's times minus 39, correct? So it's cosine of 40 times minus 39. You just have to be careful. So that but the question is pretty easy, I hope, right? Good. You have it, guys. You understand? You have any questions before I erase this particular solution? Okay, good. No questions. Wonderful. Now do the next exercise. The derivative of m at 0. Derivative of m at 0. M at 0 does not exist. Nassim. Okay, let's see. So first of all, derivative of first I take derivative at x, and that would be derivative of square root is 1 over 2 square root of gx multiplied by g prime x, and I do it at 0, right? So what is m prime of 0? It means 1 over 2. What is g of 0? G of 0 is root of 75. 2 root 75. Yeah. Multiplied by what's g prime of 0? G prime of 0 is minus 15. So it's minus 15 over 2 root 75. Good? So you just have to be very careful. Let's clear. Now your next task is n prime of 1. All right, we ready? So you agree, guys, that this question should be, thank you, Nassim, right? This should be, it's just annoying. You have to be careful not to mix up values in the table. Yes? So if there is such a question on my exam, please write at least your work, so that, because I don't really care about the table too much. If I see that you got the idea, I will give you the credit. If this question is there, I have no idea what questions will be there. So this is just product rule. So we have n prime x is f prime. I'll just write f prime g plus f g prime. Yes. And then I look at the value 1. So what am I going to have here? So I'm going to have f prime at 1. Okay, let's see. F prime at 1. Okay, ping, ping, thank you. You see, you get so many different values. My God. Hopefully, your grade would be more like 104 than 59, right? Or much lower. Oh my God, you really have a spread of values there. I see. Okay, so let's select which values can we have here. So f prime of 1, I look at 1. F prime of 1 is -1. So I put a -1 here, yes? -1. And then I have g. What's g of 1? G of 1 is 49. Plus, now I have f of 1. F of 1 is -3. Correct? Multiplied by g prime of 1, which is by -36. Good. So what we have is, we have here -49 plus what is it? Plus 90 plus 18. Good. Good. -49 plus 90 plus 18. So that would be what? That would be -31 plus 90, which is what is it? Which is 50. 59. Sorry, yes, 59, right? Good. 59. Good. Understood. What somebody wrote there. Good. 59. So I'm clearing this. Clearing it. Good. Everybody has it. Understood. Now we're going to do the quotient rule, or if you're tired, we can move to something else. It's really annoying. So now the quotient rule here, right? What's p prime of 3? So if you have such a question on the exam, make sure to show me that you followed the expression correctly, right? Who knows, maybe you mixed up some values or placed them afterwards incorrectly, but at least show me that you would have known where to look for the values.
Professor, we can see the table.
Okay, so you recorded it. It's p prime of 3. Where is the quotient rule? Here you go. Yes, that's right, Nassim. And all you have to do is, I think it's for the value 3, right? Just place the value 3 here. So what we have is, we have that p prime would be g f prime minus g prime f divided by g squared, and we need to evaluate them at 3, right? So p prime of 3. What is g of 3? So I look here. There is no 3 here, is there? Right. So that's what you call it, a mandatory reduction of your grade question, right? So you just leave it like that. Good. So now we are interested in the derivative of q at 0, where q is g that has eaten f at 0. Okay. So I'll just write here for your convenience that q of x is g that has eaten f of x, and we want q prime of 0. Oh, 4. What do you know? Good, good. So all of you are in agreement. So what is that? That's supposed to be g prime of f multiplied by f prime. Now that would be g prime. I'm searching for f of 0 here. And here I want to take the derivative of f of 0. What's f of 0? F of 0 is minus 1 minus 1 into g prime is 12. So first number is 12 multiplied by f prime of 0, which is minus 3. Good. So the answer is minus 36, as I think 4 people correctly identified. Good, or 3 people. Okay, good. They get a bit annoying. Do you want to do r prime of 0, or you had enough of this? I don't know. You want to do it, whatever, right? There are more questions. Maybe then you have to find find the equation of the tangent line. This is a little bit different. Yeah. Let's forsake the r prime of 0 and do the tangent line. Do you agree? This question is also wrong. There is no x equal to 3 there in the table. Just a second. That cannot, we're saying it's constant, Christian, so you have to be careful. You need to find the equation of the tangent line. So here there is no x equal to 3. So let's say I'm just trying to see what other value better to take it, if there is a value here. So maybe 1. So what is it at 1? F no 0, f of 1 is -1. No, -1. All right. Let me know. Yes. So we can do it only formally. I don't see x equal to 3, right? So maybe another x is meant, but then it has to solve this equation. Something cubed plus something else cubed. The x and y cubed must be equal to whatever. So are you ready? So first of all, let me write it on a separate board here. So we have this equation. We have x cubed plus y cubed is supposed to equal to fx gx. Yes? So that means that if I take the derivative with respect to x of both sides, that would be 3x squared plus 3y squared y prime equal to the product, so which would be f prime x gx plus fx g prime x. Yes? And now what we have is we need to solve for y prime. So y prime is equal to f prime x gx plus fx g prime x minus 3x squared divided by 3y squared. Agreed? That's the derivative, and we're interested at some point x equal to 3. Right, so it's x equal to 3, which means y equal to, I do not know by this information because I do not have x equal to 3, I cannot solve it. Y equal to y0, right? So this would be, in general, it would be, let's call this the slope when you replace x by 3 and y by y0. That would be something like f prime of 3 g of 3 plus f of 3 g prime of 3 minus 27, because it's 3 times 3 squared, 27, divided by, I have no idea what y is. So the solution for y should have been then something like 3y0 squared. That's my equation of that's the slope. And that should be multiplied by x minus 3 and plus y0 is equal to y. That's an equation of the tangent line. Or y minus y0 equal to this thing. I just need to know the point on this curve. So there is this implicitly defined curve, and I have that x is equal to 3 and y is unknown to me because I do not see what is 3 in the table. When x is equal to 3, I don't see it, right? You can try maybe the same thing at x equal to 0, for example, right? Maybe they meant x equal to 0 or some other number, and then I can figure out what y must be. Good? So if it were at a different point, you understand what I'm saying? So for example, if I had x equal to 0, and then I plug everywhere 0 instead of x, and in the original equation, it would be y cubed is equal to those numbers. Good? All right, so let's go onwards. All right, question 3. So suppose that the derivative of f is root of 1 plus x to the power of 4. Your goal is to find derivative of f of x squared.
Professor,
Yes?
is this a integral problem?
No.
Oh.
Where this? No, you have to find the derivative of f of x squared.
Okay.
You see, just the derivative. You know that the derivative of f is root of 1 plus x to the 4. Your goal is to find the derivative of f of x squared. So this section, it's D. You see, D3, it's all derivative questions.
Okay, thank you.
Sure.
But wait, don't we have to find the reverse derivative or no? Because
That's
this is
not
the derivative.
No, because the question is to find the derivative. Notice there is f prime, and the question is find the derivative of f composed with x squared. So just differentiate it and then use this formula.
Okay.
To complete it, yes. Okay, good, Rachel. Okay, Christian, the same then, okay. What about the rest of you? All right, are we ready? Okay, so let's look at it. The derivative of f. So first I write myself the formula. So the derivative of composition, it will be the derivative of f at x squared multiplied by the derivative of x squared, which is by 2x. The derivative of f is root of whatever number is inside to the fourth power. So it's root of 1 plus x squared to the power of 4. Why? Because what it says is that whatever number I find inside of f, okay, so it's root of 1 plus x squared to the 4 multiplied by 2x. So that would be a root of 1 plus x to the 8th power multiplied by 2x. Good? So the next question, we can return to it. The next question is about related rates. How many of you have read my notes and looked to the video that I have available? If you're interested, we can, of course, return to it and I can explain to you what related rates are. Usually, it takes more than the lessons available to get it right because people tend to not understand it. That involves quite a lot of thinking compared to other questions. Okay, so I will skip it for now. I will go to the next questions, and if you would like to return to them, we'll discuss those questions. Good? Here is question D4. So before I move, actually, guys, have you tried to look through the video on related rates? Have you seen my notes that I posted on related rates? There are two things. There are notes that I wrote for related rates, and there are questions. So one person said yes. What about the rest of you? Okay, so then let me just quickly show you what you should read. You can watch the videos that I have. There are several videos of that, and you can read it. So that's also the notes. Look at it. Here, number 6, related rates. And actually, the first question is indeed about spill. You see? So I try to explain to you what the idea is. It's just 12 pages. Not so much to read. 12 pages written with my wonderful, exceptionally beautiful handwriting. Yes? So read this thing, think about it. And here, if you're interested, I show you how related rates are applied in physics. So that's a bit more complicated. So you even have 11 pages because I'm sure you're not going to go here. Right? So that's what you should do. Okay, so here is question number 4. Question number 4. So Alexa, I sent a few emails with the videos that I suggested to watch. And this is just the related rates section 6 in my chain rule segment, okay? So here is your next question, D4. A student claims that the derivative of 2x is x times 2 to the x minus 1. Use the graph of y equal to 2x shown below to explain why this is not true. So you look at this thing and you tell me, why is that not true? Let's see. Oh. Guys, remember, very simple. What is the derivative? So this curve is the graph of 2 to the power of x, right? You see, what the question is asking, suppose you look at this graph is y equal to 2 to the power of x. If this is indeed the graph, could it be possible that the derivative of 2 to the x is x times 2 to the x minus 1? Explain why. You understand? The graph is not of, this is not the part graphed, right? 2 to the x is graphed here. And some student claims the derivative is x times 2 to the x minus 1. Very simple question if you realize what is the derivative? What are you paying attention when you look at this curve? The value is increasing. Nassim, be more precise. What value? It's unclear what you mean. Value is increasing. What value? here is a hint. What is the derivative? You know, when you look at this curve, I mean, you have to look at the derivative, correct? Because they're saying the derivative of this curve is x to the power x times 2 to the x minus 1. So in particular, you're looking at the derivative. That's what you're trying to investigate. What is the derivative? What am I looking at when I stare at the graph? Slope. But and where can I see slope here in this graph? How do I look at it so that I will be seeing slope? You understand, guys? The question is obvious if you realize what you are watching here. If you're just seeing a curve, so what? What are you staring at to read the slope? Sorry?
It's tangent line.
Yes, but tell me specifically, how do I see the tangent line, or what am I looking at when I look at this graph to see the slopes? How can I look at this graph? What should I do to it so that I right away see what sort of slopes it has? You see, guys, when you say tangent line, you know, do you see it? You see, so those are just words. Don't throw around words. What should you look at when you look at the graph? That's not bad, but the zero is a good idea, but be more precise about it, Christian. You see, when you say plug in zero, I ask myself, plug in where? And what should I observe? Yes, so the slope should be zero. You're right, Christian, right? So let me tell you how I view this graph very quickly, guys. You see, when you look, this is what you have to understand. We have a curve. If we're claiming this curve is differentiable, what am I truly claiming visually? I'm claiming that this curve is built up of many line segments. Yes? It's really just a chain of line segments. Do you understand, guys? When you say tangent line, slope, what am I truly observing? I'm imagining that this curve is just a segmented. It's like a spine. It's built of many line segments, microscopic line segments. That's an approximation to the idea that the curve is differentiable. You understand? Is that anywhere you look, you zoom in, you see what you call a tangent line. What's the tangent line? Is just the idea that there is a line that approximates very well that curve locally. So it's made of many thin small line segments. Good. Now, what do you observe about all those line segments? When you take the derivative, you're just talking about the slopes, right? The slopes are positive. Do you see that? Slopes are always positive because the lines are always, if you move from the left to the right, the lines are all oriented that they are pointing upwards. You're climbing. Yes? Slopes are positive. But if you look at this formula, will that imply that slopes are always positive? So for example, if x is less than or equal to 0, 2 to the x minus 1 is always a positive number. But x itself will make it a negative slope. You understand? This can be negative. Can be negative. or 0. So Christian answered it correctly. If you look at 0, the slope at 0 is positive, right? Whereas if this is the correct derivative formula, it tells you that at 0 the derivative is 0. So you're saying you're observing a horizontal line. But more generally, this formula gives you negative values. For negative x, you get negative values for the slope, but that's clearly inconsistent with the picture where all the line segments are pointing upwards. Is it clear? So guys, I see one person shaking his head and the rest I have no idea. So we explained this idea like a billion times, right? This entire semester I explain it again and again and again. Do you understand it?
Can you explain one more time?
Sure. So maybe better you explain to me. What does it mean for the curve to be differentiable? It means that the curve consists of, can be viewed as a chain of line segments, like what I draw here. Linked line segments, right? So what's the difference between a line and a curve? A line is the simplest possible curve because you only need 2 points to know it, right? Now other curves you need more than 2 points to know about the curve. So you can imagine that a curve is just a bunch of line segments attached next to each other. And anywhere you zoom in, you will see, here is the idea. How can I make a curve out of this pencil? I can imagine breaking it in different places and folding it in the shape of the curve. Where I break, I create more line segments. Can you imagine that, guys? So you can take a stick, a very thin stick, and that's a line. And then you can break it in certain places to make it, to flex it in other shapes. So you create more joints in that line. Right, so the idea that the curve is differentiable means that anywhere you look, I can kind of continue breaking it and the joints are slightly modified. The joints like they were here, slightly modified, slightly modified, slightly modified. Good? Intuitively, you have to have a good intuitive picture. So intuitively, any curve that is differentiable is just a connection of line segments that smoothly transition. The slopes between those line segments smoothly transition, right? So something like this is not differentiable because you cannot achieve smooth transition, you see? So but something like this, you see the line segments, they change gradually. Yes? So you have this notion that it's built of line segments. That's how you understand what a derivative is. So this derivative here, the slopes could be negative, whereas here, anywhere I look, the slopes must be positive because you can see the curve is always climbing up. Good? So do you understand, guys? Confirm if you understand the explanation. You have to have this picture in your mind. Otherwise, what you do is derivative, tangent line. It makes no sense, right? You have to just have a clear connection to the concept. Okay, so only what, 2 people understand? If you don't understand and you have questions, please feel free, just ask it, right? But you need to communicate to me what you don't realize. So like 3 people, I have how many? I have supposedly 10. 3 out of 10 understand it, or if you don't understand, ask me questions. What bothers you here? Okay, good. Okay, Ping Ping, take care.
Professor, can you explain? You kind of lost me at like the pen example.
The pen example. Okay, yeah. So what do you do to create a more complicated curve? Think about it. I hold a pen because the pen is supposed to indicate a straight line segment, right? Guys, here's what you should figure out. Why do you use tangent lines? Why lines? Lines are very simple curves. You only specify 2 points and you know everything about that curve, correct? 2 points. You can see that easily. See, I'm holding 2 points. You can mentally connect those 2 points with a line segment. Yet, you see, because you can connect them mentally with a line segment, that means that 2 points determine a line. Now, a quadratic you cannot figure out. A quadratic, it has extra degree of freedom. So you need 3 points to understand a quadratic. You need 4 points to understand a cubic. You need 5 points to understand degree 4 functions, quartic or whatever they're called, right? And onwards. So you can see that there is an increase in complexity. Now, in general, you can think of a curve as being constructed out of a line segment. What you can imagine doing is you imagine taking another point, you take a solid line, and then you imagine breaking it somewhere. Okay, let me maybe draw you another picture of that. You imagine that you are breaking the curve somewhere. So let's say you're trying to create this type of curve, right? So you can begin with a line segment like this, and then maybe here you break it. So what happens is that as you break it, you just have something like this, and then like that. Okay, you're trying to imitate this curve. Does it make sense? Now it's not a good imitation still, so I'm going to break it here and here. So now I'm going to have it increases like this, then it increases like this. Maybe a little lesser angle. Then it increases like this, and then it increases like this, and then it increases like, oh, kind of, a second, so like this, and then increases like this. So those are the points at which I broke the line, and I folded. Yes, you understand how I think of it, right? I think of taking line segment and breaking it, and then the segment I can adjust. And I continue breaking it again and again and again. I create, so to speak, infinitely many breaks, right? If the curve is smooth, then the transition between the one slope and the next slope is becoming less and less, right? The transition is getting smooth. Whereas if the curve is not smooth, the transition, let's say if the curve was something like this. So you see there is lack of smoothness here in the transition. So as I increase the number of breaks, there is going to be, between this slope and the next slope, there is always going to be a very noticeable transition. You follow? No matter how many times I break it, there is a noticeable transition. Do you understand what I mean, guys?
Sure do. Thank you.
Good. Are you sure you can see it, right, guys? So
yeah,
means there is if I create enough breakages, right, between one frame and the next, there is no there is very little transition. It's the same thing that you see when you have videos. Between one frame and the next frame, there is little transition, and the transition happen gradually. But curves that are kind of like this, no matter how much I break, the transition from this segment to whatever next segment will be at least like with the angle I drew here. There will be a significant, very noticeable jump in the slopes, and that's non-differentiable, right? But regardless, I visualize my curves as lots of line segments attached to each other. Very small line segments, so you have lots of breakages, and they attach to each other. So I can use the broken line to simulate curves. That's how I think of calculus. I built it up of broken line segments. Make sense?
Yeah, it makes sense.
Great. So now let's go on to the next question. Well, Christian, this study guide, it's on the Brooklyn College website. I think I also emailed it to all of you in one of the emails. So you just go to Brooklyn College and write uniform finals. There is also, by the way, on the website, My Open Math, they have, I think, opened a practice exam in addition to this thing. Okay, so I send it in email. I might send the email again because maybe some people didn't open it. And yeah, well, nice seeing you. Take care. We'll continue with the next question. So you have graphs, f of x is solid and g of x dashed are shown. Here are the graphs, okay? So this is f, the parabola upwards, the smile is f, and the frown is g. Now your goal is to find the derivative of the product at 4. Can you do that? The sign, not the derivative. You have to only tell me if it's positive or negative, this derivative. You understand? In other words, if the slope is pointing up or down. Well, for first, let's see. All right, so the sign could be 0, maybe it's 0, but we are looking at f times g prime of 4. Right, f times g prime of 4. So let me know when you're ready. Okay, Carolina, I'm losing you too. Okay, Alexa, you too. My God, I'm losing everyone. Oh my God.
So shocked.
Sorry?
And I'm so shocked.
Well, I'm not shocked. Yes. I actually thought maybe you'll be the only one showing up. Well, at least I recorded it, who knows? What are you writing there, Rachel?
I'm setting it up like product rule.
Yeah, okay, set it up.
So I think it's going to end up being positive.
Yeah, of course. All right, so you see, do I need to explain or you see why? I guess who knows, for possible posterity. So what happens here is that this is f prime at 4 times g plus f times g prime. Now f at 4 is 0, right? So it doesn't matter what g prime is, even though it's clearly positive here at 4, right? So really I can write f prime at 4 is clearly clearly positive. Slope is positive, right? And times g, which is a positive number, plus f is 0 times g prime is also positive there, right? Slope is upward. So clearly that is positive. And now there is the quotient rule, right? At 0. Can you do that?
I think it's negative.
Let's see. Let's see. So what is this thing? So the denominator it's g prime, sorry, g of 0 squared. Then we have here g f prime minus g prime f. Now at 4, sorry, it's at 0 now, right? So the bottom is obviously a plus. I'm supposing, let's say, whereas g0 squared, yes, so it's some sort of plus, and then g is negative, right? G of 0 is negative, so it's negative multiplied by f prime of 0. F prime of 0 is also negative.
Oh, wait. Why is g of 0 negative?
Because at 0, g is the dotted line. It's negative here. So g of 0 is somewhere here. It's like -5 or something.
Oh, I was looking at the x-axis. Okay.
Right. So g of 0 is negative. F derivative of f is at 0, it's negative. And then we have minus g prime at 0. G prime at 0 is positive, right? Because it's increasing. And then f of 0 is actually 0, right? So it is a negative by negative divided by a positive, right? So that makes it positive as well. So this is positive and this is positive. You agree?
Mm-hmm.
Yeah, makes sense?
Yeah.
So what, question 6?
I already did question 6, but if Aaron wants to do it, we could do it.
Okay, does Aaron want to do it? So we can skip it if I suppose, let's say, I don't see Aaron saying much. So I guess we go, let's see. Okay, skip away, good. So what question do we go to?
We could skip to, yeah, the uses of derivative section for me.
Okay, use of the derivative.
I did U1 actually.
So you know it, you don't need me to help with it?
No, I think I'm good.
Okay, where else?
I didn't do U2 and on.
Okay, I think U2 is a band, Irish band, if I'm not mistaken.
Huh?
Yeah, exactly. I never listened to their music, but if I'm not mistaken, U2
Oh,
is an Irish.
U2. Oh yeah, I think they had like a whole scandal that they like downloaded their music onto Apple or something like that, like Apple devices. I remember. Yes, they are an Irish band. I mean,
Yeah,
I'm not Irish actually.
very famous because I never listened to it, but being in Ireland, I've seen many advertisements of them.
Ah.
Yeah. So some values y f of x, f prime x are given below. Assume y f of x and all its derivatives are continuous for all x. Okay. So we know that derivatives in the function are continuous. Which intervals are certain to contain a solution f of x equal to 0? Defend your conclusion. Okay. F of x equal to 0.
Oh. 5 to 10 or 10 to 15.
Yeah, so there are several intervals. It's a bit annoying to kind of look at through all of them, but because it's each intervals, right? I'm hoping the question will be a little, because you have so many combinations, right? So f of x equal to 0 will exist between 0 and 5, for example. Do you see? Between we f of 0 is -3 and f of 5 is 8, so I cross the x-axis, right?
Oh, I was thinking F prime X. Okay, yeah, fine.
Right. So there are many intervals here that would work, right? From 10 to 15, you descend from 10 to -5, so you have to cross the x-axis from 15 to 20, all right? So there are many. It's a bit of annoying. And then when you say intervals, I can say interval from 0 to 5, or from 0 to 10, or from 0 to 15, or from 0 to 20. It's almost like a combinatorial problem. So
But
there are many intervals.
It can't be 5. It can't be intervals 5 to 10.
Yes, it cannot be between 5 to 10, but they say which intervals. It's a bit vague, you understand? Intervals, I can say between -infinity and 20, right? But I'm assuming they mean between 0 and 5. There must be a solution, and between 10 and 15, and between 15 and 20. Do you agree?
Yeah.
So there are like the principal intervals that I should mention, I suppose, from 0 to 5, from 10 to 15, and from 15 to 20. But the question is vague because actually there are infinitely many intervals. You understand? So
Yeah.
yes. Okay, so this part is good.
Yeah.
Yes. Which intervals are certain to contain a local maximum value of f of x?
Value of F of X.
A local maximum, right? A local maximum that we. So what?
I don't know. Is it 5 to 10 or 10 to 15 or?
Well, let's see. So that's so are certain to contain a local maximum. So first of all, we know that the derivative f prime will be equal to 0 between, for sure, between 5 and 10, right? Because slope is minus, then it's plus, right? So if all of them are continuous, then you can imagine applying the first derivative test, where I go first time decreasing, certain to decrease, and then maybe I will increase. So I'm certain to contain at least a local minimum between -2 and 3, right? And between 3 and -2, so my derivatives must be positive until I reach. So there is a 0, right? And then they become negative. So between 3 and -2, I must have a local maximum, because the derivatives are positive all the way until they reach 0, and the negative afterwards, I suppose. Again, but certain. It's all basically plays on the intermediate value theorem, so you just have to be careful with this question, actually, right? So local maximum, local minimum is so they say local. Local, I suppose they mean excluding those values. So basically, in terms of the derivative shape, right? If I graph the derivative curve, how do I will identify a local maximum? The derivative does this when it say if this point is a point, call it point A. How would I identify that the first derivative gives me a local maximum there? It would be a graph that looks something like this, right? If I move from the left, that's the graph of the derivative. The derivative is positive at A, maybe it's 0, and then after A it's negative. So when I see the curve kind of cuts through without so this means that if this is the graph f prime, right, this means local max at x equal to A. Make sense? Because if I were to draw A here, we are increasing as I move towards A and decreasing afterwards. So that the derivative is negative. So this is the graph of the derivative, right? So the graph of the derivative has to go and do this for local maximum. If I have something like this, then that's just a rest point, right? The derivative was increasing, stopped. So that means the curve is kind of increasing, stopped, and continued increasing. So that's a rest point. It's neither maximum nor minimum, right? If that's the graph of the derivative. Good?
That's the inflection point?
No, that is the graph of the derivative. That's all it is, right? So what it is, I'm just saying that it's neither max nor minimum, right? Inflection point has to do with derivative changing sign, but with the second derivative changing sign, right? So that means, was it an inflection point? Actually, let me just go through it. Okay, so if you see something like this, and that's the graph of the derivative, it bounces back up, right? What does it mean about the second derivative? The second derivative, then here, it was negative but becoming less negative. So that means that it was negative but becoming less negative. So that means that second derivative was positive near that point, right? Second derivative was what's the second? What am I saying? So second derivative of this curve is negative, because you see it's negative here, and here it is 0. So negative here is 0. That's second derivative, and then afterwards, second derivative is just the slope of the f prime. That would mean it is here positive, right? So that is your right on inflection point, right? Because the second derivative changes from minus to plus. If the graph is so to speak in reverse like this, kind of bounces back, then the first derivative, this is f prime. So the derivative of that is positive. So then you would see something like derivative is positive and then negative. So you would see something like that. That would also be an inflection point, right? So that's if the first derivative kind of jumps back up, right?
So the answer to which intervals are certain to contain an inflection point on the graph y equals f of x would be 5, 10.
It's so 5 and 10. Okay, so here that you say the derivative was initially, it had to cross 0, right? 5 and 10, it was negative, had to equal to 0, and then you know, yeah. So I would say 5, 10, because the graph, the derivative was negative, had to go through 0 and become positive. So at some moment when 1 second, submit 5, 10. I can clear it, yes? So you say 5 and 10. So the derivative was negative at some point. Negative, and then became positive, right? So the thing is the derivative could simply cross once. It could cross once, right? And that would mean that there is no inflection point. Second derivative doesn't change sign, right? All that means is this: between 5 and 10, it means that at least one time the derivative was equal to 0, right? So the derivative has to behave this way to create inflection point, either like this, kind of hit 0 and go back, or like this, hit 0 and go back. That's the first derivative. I'm saying it has to look like this. We don't have any second derivative, so first derivative must locally make this U shape to create inflection point. Yes. So for that, yeah, I don't see why there should be a certain inflection point for this information. It seems like you can always cross through and return if you have to. So the local maximum, local minimum are kind of easier to judge here, right? That you must have it, but the inflection point, not so much. One second, let me think. Let me think for a second. Doesn't. Inflection point are defined how? That this only that that must you remember must the first derivative equal to 0 for this to be an inflection point, or simply the second derivative changes sign?
I think the second derivative has to change sign.
Yes, but if it's continuous, that's the thing. If the curve is continuous, for the second derivative to change sign, it must. Okay, so second derivative changes sign. So then that would happen for whenever the first derivative is like this, or like that, because here you see second derivative will be 0 and then change sign, 0 and change sign. So any heel doesn't have to go through the origin. So actually, by continuity, pretty much, let's see what I can say there. By continuity, it would be the minimum of the curve or the maximum of the curve. So pretty much anywhere between 2 points where the minimum and maximum are not those values, it will be not the end points. There will be an inflection point, at least one of them. Okay, so that means what for this case? Let's say between 5 and 15, for instance, there will be for sure an inflection point, because the maximum is not 5 and not 15. So between 5 and there is a change. So and you can be bigger than this value. So between 5 and 15, there will certainly be an inflection point. Make sense?
Yeah, because it changes from concave up to concave down, basically.
Basically, the extreme value theorem, it's differentiable everywhere. The extreme value theorem guarantees that there is an absolute maximum and an absolute minimum for any curve, right? And as long as that absolute maximum minimum do not occur, and the curve is differentiable, as long as it's not at the end points of the interval, then that maximum point must occur in between them. So, and its derivative at maximum must equal to 0. You see, because if you climb maximum, you're climbing a smooth hill, you must become level parallel to the x-axis. And the same thing with the minimum. So between 5 and 15, the maximum is bigger than -2, which means the maximum is between 5 and 15, which means the maximum of the derivative equals to, derivative there will equal to 0 between 5 and 15, for instance.
Okay.
Make sense?
Yeah, that does. But just to go over one thing, if f double prime if f double prime equals 0, that means there's no inflection point. Because it means
no,
that,
I mean, if f double prime, so inflection point is where the second derivative changes sign, you said, yes?
right?
So it can, if f double prime is a continuous function as well. We're told all derivatives are continuous. So if it's to change from negative to positive, it has to equal to 0. So the inflection points of f double prime occur around the points where f double prime is 0.
Okay.
Make sense?
Yeah, I think I have to go over a lot more graphs of these.
Yeah, this is not an easy question, actually, right? So you just have to kind of, good?
Yeah. It's a lot more like you have to break it down and visualize it or draw it out yourself.
Yes. So I'll clear it. You want to solve one more problem or something? So you understand how to, the idea is you get it from here, yes?
Yeah.
Yeah.
Number U3 doesn't have it's a drop down and doesn't say what it's supposed to be.
Okay, suppose the only critical values of f prime x are x10, 20, and 30. And okay, so you guarantee,
It's probably maximum, minimum, and nothing.
I don't know what they're asking. Based on this information, you guarantee that at x10, so we have only critical values, right?
Yeah.
X10. So okay, at x equal to 10, the derivative is equal to 0, and second derivative is equal to -9, yes, at x10. So that means that that because it's in negative, it means that second derivative test tells us that we have a maximum at 0, a local maximum. You see why? Because the -9 means that second derivative wants to make the slope negative after 10, right? And before 10, it is basically near the number 10. Second derivative is trying to make the slope kind of more and more negative, which means you were climbing. Look at it. You see how it happens. This was the slope a little bit before you hit 10. This was a slope slightly less positive later on. Then at 0 it was flat, and then it will be negative. So you're tracing a maximum. Yes, so at 10 it's a local maximum. At 20 it is a local minimum because the second derivative is positive. Yes?
Mhm.
Yeah, I need to try to explain it to those students. I haven't gotten over this information, and I have a feeling none of them bothered.
And that at x equals 30, the second derivative is 0.
Yeah, so second derivative is 0. It means what? Well, I guess we have an inflection point. I presume if it's, of course, if they are continuous.
So since it's 0, we're going to have to do the second derivative. We're going to have to do the first derivative test. We can't.
Yes, we do not know if we have maximum or minimum. At 0, we only know we have a critical point. It could be that the second derivative was slightly negative before we hit 30, and then positive. In which case, yes. In which case, what? In which case, the slopes were kind of. You see, the slopes were. You see, even using the second derivative test, I suppose you can kind of figure stuff. If the second derivative was slightly negative, if it was negative below 30, that means that that my derivative here was positive, right? Was positive, and then afterwards, if it's slightly positive afterwards, you understand. Basically, even using this, if I know something about the second derivative, I can infer what happens here as well. So they say use the first derivative test because you see, using second derivative, you have to infer about the slopes of the first derivative and then to conclude. So it might be like an extra complicated effort.
So is it
It's not known because you see, I need to know more about how the second or the first derivatives behave around 0. If I know how the first derivative behaves around 0, then I can conclude if it's a maximum or minimum. If I know how the second derivative behaves around 0, I will be able to reach the conclusion about this derivative, about the first derivative, right? If I know an interval of second derivatives, I'll be able to figure out an interval of first derivatives, right? Infer, and then that will tell me if it's maximum or minimum. So that's why they say use the first derivative. But using second derivative, I can infer information about the first. Because, for instance, let me just explain, right? For this guy, let's say second derivative is 0. That's f double prime, right? And let's say that what we observe is that it was positive here and negative afterwards. The second derivative was positive 0, and then negative afterwards, right? What does it mean? It means regarding the curve, regarding the first derivative, right? So it means that my slopes for the first derivative, they are now 0, right? So if it was positive, if the second derivative was positive before, that means that it was driving the first derivative to become 0, but it was negative. So first derivative was kind of like this. The curve was negative, right? And this was trying to make it more positive. It stopped trying to do anything at 0, but it already succeeded to achieve 0 here. And then negative, second derivative is negative, so it will now turn the slopes like this. So now this means it's neither maximum nor minimum. Do you see that?
Yes.
On the other hand, if I have positive, if I have positive for the second derivative, yeah, positive means it was successful. It rested at 0. It was making the derivative before the first derivative. It was making it to make the first derivative equal to 0. It had to make it less negative, right? So the first derivative was negative before it, and then at 0 it rests, and the second derivative rests. And afterwards, for the next lines, the second derivative will make that 0 derivative positive. It will make it grow. So the slopes, you see, I'm kind of representing line segments and slopes, so that traces a local minimum. So if first derivative is positive and 0 at 0, and first derivative is 0 there, then I'm expecting that it will be a local minimum. Make sense? If, of
I
course,
think I have to
that's
think
very,
about it.
very, very important. If, of course, the derivatives are all continuous functions. If I know that they're all continuous functions, then I know that first derivative is changed gradually, right? So let's see about it, right? So at 0, nothing is, no pressure is happening for by the second derivative. But let's look to the values below 0. The values below 0, if the second derivative were positive, what it was doing as you approach 0, it was trying to make, because how can it make the first derivative equal to 0? By being positive. It must be that that the line segments that make the actual curve were with negative slopes, and the negative slope was becoming more positive. That's what the second derivative is doing. It's the negative slopes are becoming more positive, right? Because you see, they have to reach 0. By becoming more positive, if they were positive to begin with, they could not be 0 because they would just be more and more positive. If there is continuity, of course, of the first derivative, right? And of the, you understand, if the second derivative is continuous, then first derivative must be continuous. Good. So they're becoming more and more positive, and then they reach 0. And then afterwards, the second derivative continues to try to make it more positive. So the next slope is going to be more positive than 0, which is positive slope. And I trace a sort of U shape.
But at 35 to the right of 0, it's negative.
Sure, but that's a lot of numbers between 30 and 35. This is only locally, right? So they can switch very rapidly. But the point is that in a small neighborhood of 0, the slopes are, if it's continuous. I see if there is no continuity of derivatives of second derivative, then this conclusion is not true.
Okay.
Right?
I'm gonna go review those.
Okay. Sounds good.
Yeah.
All right.
I'm good.
Okay.
I'm gonna go.
Goodbye.
Have a good day. Bye.
Bye. And then there was 1. No, 0? What do you mean, you're leaving? You want to turn the camera on, I think. I'm gonna stop the recording.